Hi guys, and welcome back to Introduction to Mechanical and Automotive Engineering. I'm your lecturer, Dr. Elizabeth Kyriakou, and today we're going to take a look at how to put together your 7-minute presentation for the Design Studio component of this course. And what I'm going to go through today is actually the PowerPoint pack that I've put up on Canvas, and let's just take a look at the first slide. So what we have here is, first slide is just a list of instructions. So basically, you don't need to change this PowerPoint presentation. All you need to do is add into your own data, and where it says delete this page, when you're actually saving your file, it will just be a smaller file size and easier to upload if you just delete the extra pages that I've actually included in there for you for instructions. It's a 7-minute presentation, and it's pretty much a PowerPoint slide with a voiceover on it, and in the next slide I'll show you how we can do that in a really simple way. After 7 minutes your presentation won't be marked. The idea of this is to actually deliver the information that you need to effectively and efficiently. Before you speak, it would actually be nice if I knew who was speaking, so just introduce yourself. And I'll just add that not everybody in the group has to speak. A nice guide for talking is 1 minute is about 150 words. So basically with 7 minutes you have about 1,000 words for the whole presentation. So you should be able to plan each slide according to how much time you want to spend on it. Throughout the presentation and at the end of the PowerPoint pack, there is some data that you'll need to use to draw your graphs. What else do we have here? So you'll be marked on your presentation content and not your presentation skills. Okay, so I'm really looking for some good content here. I've just spoken about where the data is for the bridge compression data, and that is up on Canvas or on this slide. I think you should be able to use Excel to analyse all the data in this presentation, and it should be pretty simple. We've done a few classes on Excel, so you should be okay. Finally, I've asked students to fill out the contribution table, which is later on in this presentation, and there'll be a separate upload for your logbooks. And basically, I'm only going to take a look at the logbooks if there is a dispute in your group. So we need to know, keep a record of who's doing the work. And finally, this is due on the 18th of October. So just a simple upload to Canvas. Okay. So the next slide is how to record your presentation. And this is just pretty simple. We have I've just shown you that you can actually hit the slideshow button in PowerPoint and record the slideshow. And this is kind of nice because you can actually do a recording per slide, so you don't need to start from the beginning if you've made a mistake. And that's about it for the recording. You should be okay with that. And here's the rubric, and I thought I'd start off with the rubric. So there's pretty much 3 components to this presentation. You have the theory, so you've got your hand calculation versus the modelling, and you've got the road analysis, which we'll go through. The next part is the results for the tensile testing laboratory. You need to draw some stress strain curves. And finally, we're going to take a look at the bridge testing analysis. So this is 3 parts. You're going to draw 3 graphs and give me some nice insight to what these graphs actually mean. So as you can see that each section has marks allocated to it. I've made it out of 55. So when you're answering these questions, just reflect on what the value of the grade is for that section, and then you can actually see how important that part is. I've actually reduced the grade for the hand calculations versus the modelling, and we'll do a little bit more work on the actual road analysis. So when we take a look at the next slide, this is just a breakdown of the marking rubric. So basically for all your graphs, you'll have 5 marks for how in-depth your graph actually is, and if you have all the required information, you've used to write units. And the second part of the grade is another 5 marks, is for the actual explanation. So draw me some nice graphs. And then, so the first real page of your presentation is the Design Studio presentation slide. And here, all I'm asking you to do is just to upload and just insert here what your bridge actually looks like in CAD. There are actually no grades to this part, but it would be nice when I'm actually listening to your presentations that I can see what your design was. And then, now we're going to move on to the theory side of things. So the first part, it's in 2 parts. So we have the theory versus the simulation. And basically in the next slide, what you'll do is you'll just be inserting some of your hand calculations and your simulation. And there's a few questions, you know, like, does your hand calculation actually validate the results that you get out of your modelling? And this is a very important part of engineering, where before you do any simulation, you need to make sure that you know what kind of numbers you're looking for. What parameters are important, so for the validity of your results. So are you looking at the force, are you looking at the stress? And yeah, just highlight some of the assumptions that you did make. The next section is looking at bending stress in the road, and this is what we've been doing pretty much in class on drawing shear force diagrams and bending moment diagrams. So here we have the, just go to the next slide. So here is where you upload your results. So just a quick explanation of the difference in maximum stress between the hand calculations and the modelling. This is actually only worth 5 marks, so it's not really in-depth. So here we have the actual road. And what I want you guys to actually have a look at here is, let's take a look at a bending moment question. So the road that we actually used originally was an aluminium road, and then we changed it to polyethylene for the experiment. And I thought what you could do is, here we have all the data for the dimensions of the road, and we have the weights, and I think we calculated once upon a time that we designed for 14 newtons. So this is what I'd like you to do. If you just draw the road, and we have a force going down of 14 newtons, and you're going to have some reaction forces going on. And so we have an AY, an AX, and a BY. So straight up, you can just calculate your reaction forces. Our distance here is 0.2 metres on each side, and we can just look at that and say that AY is going to be 7 newtons and BY is also going to be 7 newtons. And what I want to be able to do is, I want to be able to draw a shear force diagram and a bending moment diagram, because I'd like to find, we want to find our maximum bending moment. So what am I going to do? Here is my diagram. I'm going to actually cut the beam in 2 places. And over here, I'm just going to draw the beam. So that's 14 newtons, that's 7 newtons. I don't mind if you make the road to become a distributed load. It just means that your diagram's actually going to be different. Okay, so you'll have a distributed load on this, but this is just very, very simple to start with. So here is my axes. That's my shear force in newtons, and this is going to be my bending moment diagram, and that's Newton meters. So what are we going to do? We're going to take this beam, we're going to assume that we're going to measure from X. So I have 2 boundary conditions. I have 0 to 0.2 metres, and then 0.2 to 0.4 metres. Just write that 2. So this is going to be 0.2, and this is going to be 0.4. Just keep everything in SI units for all your graphs. So SI units. So that means we're going to use newtons, kilograms, metres. So what's the first thing that I'm going to do? I might actually just clean this part up. So I want to calculate the maximum bending moment in this beam. So the first section I'm going to look at is first cut. So here we have 7 newtons, and we have we've cut the beam, so we have a shear force and a moment. I've said that this is x metres. So if I want to find the shear force, our boundary is 0 to x to 0.2 metres. If I want to find the shear force, I can simply say sum of the forces in the y direction equals 0, and I have 7 minus v. So v, our shear force is 7 newtons. So if I go, and that's constant here, so if I go up here, I have 7, and I'm just going to have a straight line. So if now I want to have a look at the bending moment, I'm just going to calculate this value. So I can say sum of the moments around 0 must equal 0. So I'm going to have this force, and that's going negative, so I'll have 7. My perpendicular distance is x plus m. So m is going to equal 7x Newton meters. So if I substitute, so here's 0. So if I substitute 0, so if x equals 0, m is going to be 0. If x equals 0.2, m is going to equal 1.4 Newton meters. So this is a linear graph. Here's my point, and I'm just going to draw a straight line. Then the next thing that we're going to take a look at is the next half. So now I've got my beam here, and what's my diagram going to look like? I think I'm running out of room. Let's just clean this up. So now we're going to look at the next boundary condition. So now I'm going to take a look at here. So I have 7 newtons, I have 14 newtons, and here I have V and M. This distance from here to here we know is 0.2 metres, and this distance here is going to be x. So we need to find out what this distance is. So this distance here is going to be x minus 0.2 metres. So you can find your shear force by sum of the forces in the y, and you can find the bending moment equation by sum of the moments when the point has to equal 0 point. So what you're going to end up with is this graph. So I want to know what the maximum bending moment is. It's at this point. So maximum bending moment occurs when V equals 0. So when V is 0, here is 0, your bending moment is going to be 1.4 Newton meters. Okay. But this doesn't tell us anything about changing the material properties. So how can we include material properties into this analysis? So that's what we have the flexural formula for. So let's take a look. Okay, so before I go into the flexural formula, you can actually, if you choose to have a distributed load across your beam, then you have your reaction forces, and then you have the load from the car, what's going to change? When we just did a simple scenario of just a load here, we had our shear force was going to be constant here and here. And that's my shear force diagram. And my bending moment diagram is going to be like this. So what happens if I have a distributed load? Well, my graph's going to change. So here, on this, for the shear force, we're going to have a linear curve. And for the bending moment, we're going to have a parabolic. Yep. Because the distributed load is going to give me a parabola. So I'll let you take a look at that if you choose to go down that path. So let's take a look at materials. So in the previous slide, we actually said that sigma allowable for the aluminium was 90 megapascals, and sigma allowable for the polymer was 10 megapascals. So what's the first thing we need to do? We need to change these units, okay, to 10 to the 6. And how can we describe what the material characteristic is through the stress? And if we want to find the maximum bending moment, we can find it what it's going to be, because it's going to differ between the two materials. So we're going to use the flexure formula. So sigma equals my on I. So here we have it. I can calculate I, that's my moment of inertia. I know that the cross-section of this beam, we've got the data up here, is going to be simply, it's simply a rectangle. So here's my cross-section. I have 4 mils, and this is 70 mil. So I can say I equals 1 on 12 BH cubed, which you can calculate that. And then here is my cross-section, and I have a centroid here. So this is my B, that's the H, that's C. Where does my maximum bending occur? It occurs furthest away from the neutral axis. So this here is going to be Y. So if I substitute, so for aluminium and the polymer, I remains the same and Y remains the same. So the only thing that changes is, so only sigma is changing. So then I can find the maximum bending moment for aluminium and the maximum bending moment for the polymer. So hopefully you guys can do that. Okay? So for the next slide, we can take a look at So that's what I've just looked at. That's where you can just put your calculations in, and please just do not type your calculations, just handwrite them and take a screenshot and upload it. The next part is looking at the tensile testing laboratory. The data for the tensile testing is on Canvas, and all we're going to do here is, from the tensile testing laboratory, you have a force displacement graph, and you've got to convert this into a stress strain curve. So you're going to have epsilon and sigma. So the graph should look like that. And then what you're going to do is you're just going to identify like the key points. So your Young's modulus, your yield stress, UTS, and your fracture point. And you can actually put this in a table for the three different materials. So you've got metal, polymer, and fiberglass. So you can just drop a table and say you've got metal, polymer, fiberglass, and then you can have all your parameters that you calculated. And then what you can do is you can actually do the same. So this is your data, and then you can actually have a column for published data. So that's data from a textbook or from a journal paper, and you can just do a comparison between the two. And here is where you can make assumptions of why the materials properties are not the same from experimental errors, and we don't actually have what the polymer is, but maybe you can go and look up a few different types of polymers and make an assumption of what that polymer could be based on its mechanical properties. So that's pretty much the tensile testing lab done. And then we have all the bridge analysis to look at. So here we go. So this is where you explain the validity of your results. So that's what we just did, like with the table and comparing that to published data. So now we take a look at the experimental component of the bridge compression testing, and we extracted some data. So on the back of at the end of your presentation slide, you should be able to see. Let's just see if I can do this. You should be able to see this data. So basically what we have is we have 4 polymer bridges, and we only had the opportunity to build the 3D printed bridges. So if you actually did polymer laser cutting, I would use this data. And then we have 6 metal bridges. Okay, so for each bridge, what did we do? For each bridge, we recorded the maximum force that the bridge was able to take, and we also weighed the bridge, so we've got a mass. So so what you're going to be drawing up for each of these, let's just have a look at what the first slide is. So the first set of results is to draw the force versus the mass for each bridge. So for each of these data sets, which is at the end of the presentation pack, you will have a maximum force and you will have a mass. And basically what you're going to do is you're just going to plot it on a graph. versus mass. And you can do it two ways. You can either put all the data on one graph, or you can do one graph for the polymer and one graph for the metal. It doesn't really matter. And what you're going to end up is you're going to end up with a scatter plot. So you're going to have all these points. Then what you're going to do is you're going to take a trend line, and you just probably do this in Excel. And everything above that line is a happy graph, is a happy bridge. Everything below is not so happy. So what you need to do is you need to actually say which is the best bridge and which is the worst bridge and why. And then finally, what you need to do is you need to be able to identify where does your bridge sit on this. And even if you don't have accurate data